pretty much everyone who has done something very, very important in C++ is here at least every other year or so. Directly interfacing with those people is just an incredible boon to your career, especially early in your career. Getting to pick people's brains on things, just hanging out, talking with people, you can't put a price on that. And you don't get those online.
All right, welcome everybody. My name is Sunny Chatterjee. I am an engineering manager in the Visual C++ team at Microsoft, where I am fortunate enough to work on static analysis. And today my talk is going to be about how we use static analysis to drive program safety in C++. This talk is all about making it real. So every line of code that I will present today, it's actually from real shipping production software. And I would encourage all of you to participate and see if you can discover some of the bugs that we find in today's talk. With that, let's see if this works. Okay. I would like to welcome all of you to CppCon 2021. We have a booth where you can meet the C++ team at Microsoft, ask questions, and discuss announcements. We also have a survey that I would encourage all of you to fill in to give us feedback. I would like to thank the team. The work that I'm going to show today is not something that just I work alone. There are a lot of smart, passionate engineers on the team. So I would like to thank Daniel, Dimitri, Gabor, Huisang, Phil. And we also work closely with C++ core guideline editors. And I see Gabby in the room. So I would like to thank everybody that has contributed to the tool set. So in this talk, I'm going to cover why code safety matters and what is static analysis, and how you can integrate these safety checks with Visual Studio and GitHub. GitHub is something new. It's a very recent experience that we have onboarded, and I'm very excited to announce that today. In fact, a few hours before my talk, we just had a blog that went live demonstrating how easy it is for you to set up some of these safety checks in GitHub. I'll then talk about the most fun part for today's talk, which is showing static analysis in action, finding bugs in real code. And next, I'll cover where we are, what's next. And like they say, it takes a village. So I will encourage all of you to join the fun, provide us feedback, because a lot of the work that we do is heavily influenced by what we hear from the community. So with that, I would first like to cover why code safety is important. So when I asked Bjorn this question, this is what he had to say, that complete type and resource safety have been an ideal aim of C++ from very early on. And for those of you that attended Bjorn's talk yesterday and type and resource safety, I think this is something that he also emphasized in his talk. To that, I will say that great customer experiences start with quality. You can build a very polished product with all features and everything, but if the product doesn't meet the quality bar, if it has crashes or hangs, if it does not perform well on all the form factors that the customers use, if it has security vulnerabilities, then that product will not get used. So with that, I would like to say that if you just rely on the language and the compiler to build a quality product, then you are missing out. You also have other tools in your arsenal. You definitely need to rely on judicious programming rules, and C++ core guidelines is a great place to start. And like I would say, you should absolutely start using these. And if you are, my team has engaged with the guideline editors over the past several years, and they do listen. So if you want to, certain rules to be changed or framed differently, please engage. Next, I would say there is a lot of choice when it comes to static analysis. This is something that you can use to enforce some of these judicious programming rules. If you use static analysis, one of the nice things about this is it can really find defects early in the development cycle, and that's really useful. And then you have the guideline support library. It's like a few hundred lines of ISO standard C++ code that we have. It defines certain type extensions that work across every platform. So instead of trying to do annotations that are specific to a language extension, you can use type extensions and express intents in code, which you can't do using just the standard types. And GSL has been a foundational library in also helping standardization of certain types. Many of you are familiar with the C++ 20 standards type standard span, and it all started in the GSL, and I think that played an instrumental role in its standardization. So with that, I would like to move on to what is static analysis. Static analysis finds bugs in your programs at compile time. So what it does is it systematically applies some clever algorithms to look for certain bug patterns in source code and points that out to you. As you know, like in a program, there can be a number of paths. In fact, the number of paths explode with the presence of every branch. So if you try and explore every path in the program, it probably won't be a scalable solution. So you have to be clever, and you have to apply certain heuristics to only explore those paths where you see certain properties that you are interested in change. And static analysis, one of the nice things about static analysis is it can tell you what the problems are even before you have gone on to the build stage. So imagine you're typing in your code, or you're saving your work, or even when you're building, maybe it runs in the background, or even when you have sent a PR. The point here is even before you have merged your code, you can look at these defects and try and fix them, because you're already engaged with that code, and there is a very high chance you would understand what is going on and you would fix it, as opposed to your code getting merged, checked in, some bug getting filed by some traditional testing techniques, or maybe from the customer. Then you get this report back after months. The static analysis, you can do it like in minutes. It's not a substitute for traditional state testing techniques or runtime checks. It's a complementary tool. And I wanted to have this on my slide. This is like an article that came out in The Economist maybe a decade back. It's called Building a Better Bug Trap. And it's still relevant to this day. Basically, it says a bug which costs a few dollars to fix on the programmer's desktop, it costs several hundred to fix once that has made it into a program, and many thousands if it's only identified after the software has been deployed in the field. And there are many zeros in that 1,000 if it's a security vulnerability. With that, I would like to show these safety checks, how easy it is to run these. And last year, I did a live demo with Visual Studio. So this year, I just want to highlight what the Visual Studio experience looks like here. There are two things to note in this example. The first is defects should show up in almost real time. So as you can see, the green squiggles basically tell you there is something wrong with the code. You go and hover over the green squiggles, and it tells you what the problem is. And it's all happening while you're working and saving your work. So analysis is running in the background and producing these results in almost real time. And the second interesting thing about this is defects should be easily understandable, because if the defects are not understandable, then you can't do much. Like programmers can't really do much with that defect. And you find that blob of text which is not very readable. So let me just enlarge and show you what I really mean by defects should be understandable. So here, static analysis tells you that you are dereferencing a null pointer. But in a real-world code, this function is not more than 10 lines. Maybe it happens way below in an analysis path. And what we see here are key events. In other words, these are what the analysis believes to be true. It's like getting a brain dump from the analyzer. So it tells you that on line 17, for example, the authorization context, the pointer to that is null. On line 18, it believes that if condition to be true, it assumes not be condition to be true. And then on line 26, you're trying to dereference p context, and obviously you run into a null pointer dereference. So it really makes it obvious and easy for you to understand and follow what the analysis is trying to tell you. And the other interesting thing about this example, like I said, everything that I show today is from real-world examples. So this is something, this code actually was sent to me by an engineer on the Azure team. And what happens is when you use our products and if things crash, you can consent to sending reports back to Microsoft, and we call them Watson, and we get these crash reports and crash dumps. We try and fix it. It's an expensive process for software that is already shipped. And in this particular case, static analysis was actually able to find an issue that actually came back as a Watson bug from the field. Since this was just a warning and not an error, didn't break the build, the engineer working on the code base didn't fix it, and so actually it was a lot more expensive to fix. So you should really be paying attention to these warnings on the desktop. With that, I'm very excited to announce that we now have a GitHub Integration Experience. So what I'm announcing here is a publicly available GitHub Action for the whole C++ community, where you can run code safety checks and view results in GitHub Visualizer. It's built on native Cmake support, and there are a few reasons why we chose Cmake. First, Cmake has a rich set of APIs that makes it easy for us to get build information that we need to run analysis. And we also figured in GitHub, a lot of the open source projects use Cmake as their build system. So it's a popular choice. And we also believe that with Cmake, you can try it out. And if you would like this on native MS build, we have suggestion, and you can upvote that, and we will try and work on that next. So with that, I would like to share this link that just showed up in our blog a few hours back that walks you through the step-by-step process of how easy it is to configure the code scanning alerts in GitHub. You can read more about code scanning in GitHub in general, and all this is built on static analysis log format, which is called Serif 2.1. If you're not familiar with that, it's basically a standard log format that every static analysis tool writer agreed on, and it's some sort of a standard. And if your analysis tools produce Serif 2.1, you can write your own code scanning alert. So everybody can contribute and make the community better. With that, I would also like to point out there are a couple of other actions from Microsoft you might see in the marketplace in GitHub. There is one called DevSkim, which is security checks. There is a PS script analyzer it's a lint check for PowerShell. With that, I would like to point you that it's just 3 clicks with which you can set up these code scanning alerts. You just go to GitHub in your project, you go to security, you go to code scanning alerts, you click on setup code scanning, and then you select Microsoft C++ code analysis, and you set up this workflow. That's all there is to it. And the same example, if you have your code in GitHub, you now have these alerts show up in GitHub in your pull request. So this is just a snapshot of that. And with that, I would like to show you this experience live. So let me go to my pull request, which I created yesterday. All I did is port that null pointer dereference from the real world into GitHub. And now this is my pull request that adds it. So as you see here, the pull request, if I go down, okay. Let me. I think that's better. Yeah. So you can see here that you are what you are doing here is you have the code scanning set up here, and the code scanning is way here below here, where you can essentially. What we have configured is 2 alerts. One is our code analysis. The other is CodeQL. CodeQL is a query-based analysis engine. It's the default action that GitHub offers you. And so let me tell you how you can see these alerts on the code. Okay. I think what I'll do is extend my display. That way I can show the code. Give me a second here. I really want to show this. Yeah, so I'm asking it to duplicate this displays. Okay, so let me show you what you see now. You go to the files changed now in your PR, and on the files changed, you find that you have your source code here, the same example where you're trying to initialize your context. And then you have this code scanning alert in your PR that tells you, look, there is a null dereference that's happening here. It has an interesting button. It's called show paths. So let me tell you what happens when you click on show paths. So when you click on show paths, it gives you a number of steps and walks you through the analyzer's reasoning. So on step 1, it tells you, look, on line 17, p context is null. And on step 2, it tells you, analyzer assumes that the if condition is true, it assumes not p connection to be true. On step 3, it shows you that it takes the if block and calls cleanup context. And on step 4, it tells you that p context is dereferenced, but still may be null. So it's very intuitive for you to figure out what's going on in that warning. Now, if you are a branch owner, you have additional power. So you can look at this drop down here, and there are a few states like dismiss, as you see here, but you can also mark something as this is used in test. Maybe it's a false positive, and you don't want to fix it. So you have a lot of flexibility to what you want to do with these. The other thing I want to show you is if you go to the click mode details, you will see that there are 24 code scanning alerts. If you click on those alerts, these are all the alerts that are there in the main branch. So what you get shown is the issues that only show up in your PR. So it's like right there, we just show you just the change that you care about most. But as the branch owner, you get to see the whole backlog, and maybe you want to clean this baseline at some sort. You can sort them by rule, brand, severity, and the way you can configure other alerts is you click on this add more scanning tools, and you will find the code QL at the top, which is the default offering from GitHub. And you will see our Microsoft's code analysis right below here. And then you can click on the workflow. And then you just start to commit this change. And that's all there is to it. That's how easy it is to configure these alerts. So with that, I would like to summarize the whole GitHub experience. It's an ideal way to shift left, right? It's where the open source community is. So if you are a maintainer of an open source project, give this a try. It's free for all public repositories in GitHub. Like you saw, it automates static analysis runs in the PR workflow and surfaces issues to engineers before the code is merged. And if you're working on a private repository, GitHub does offer an advanced security feature, and I have a link for you to go and explore that. With that, this is the most favorite part of my talk. I'll basically show here the real bugs that we have found by applying some of these rules. And this is something that I would encourage all of you to participate, and let's see if we can find these bugs together. So in this example, you have a function foo, and I want to focus you on this line where we are calling a function f through a union. And there is a pretty nasty bug hiding somewhere here. Does anybody want to take a stab at what's going on here? What's the problem in this code? Sure, go ahead. Absolutely right. So what you said is the actual data that's being written to is in PV, but when we are accessing that data, we are accessing it through PY. So let's look at how static analysis find this bug for you. So this is a typical workflow in a path-sensitive checker. It first starts from the function entry and then tries to explore different paths. So I'll show you one of the problematic paths where this bug is found. So it first looks at the allocation of the union X, and we allocate that memory within U. Then there is a condition, and this condition is assumed to be true in this particular path. And then we are reading this stream from an external entity outside our system, and we're assigning that string to this pointer field PV of the union. And down below, at the very last line highlighted in red, is where we are trying to access that union, but through its other pointer field py, and we are calling a function f. Now, the problem here is this is an actual type confusion attack that we saw in production software. What's happening is you're reading an attacker control string outside your system, and then you're trying to call a function through the other pointer field in your union, and ending up calling a function that you shouldn't be calling. So for today's talk, Peppa is my programmer, and she was very happy that we had a Lint-style check that could find this bug for her. Essentially, all that check does is it tells her that you have an expression px that uses a union with multiple type pointers, and those are really bad. Those can cause type confusion attacks. So please use a variant. And this is in line with C++ core guidelines. So if you look at this problem space that I just showed here, I showed you a union with multiple type pointers that are vulnerable to type confusion attack, where especially the types depend on external conditions. It's easy to lose control, especially when there are multiple pointer values involved. And it's pretty common in production software. So the way you can mitigate such attacks is by sticking to a discipline where you forbid use of unions with multiple pointers and encourage use of variant. If you have this rule enabled, new code like where people copy and paste an existing structure over the code base, they can't do that, and because the rule will be flagging these issues, and it's supported by C++ core guidelines. In fact, there is a type.7 rule that asks you to not use unions but use standard variants, and it's very easy to check to implement for a linter. So the next example is again a simplified version of a real-world code, and there are many things wrong with this, but I just want to emphasize that lint-style checks can be, syntactic. They look at the compiler trees and try to infer things, or they can also do simple flow analysis. Like in this particular example, we have a warning that says symbol buff is never tested for nullness, and it should be marked as not null. And what the analyzer is doing here is really doing a simple flow analysis. It is looking at that dereference buff index, which is a dereference into an offset from, into buff. And then it's trying to ascertain if that buff is null. Now, the analyzer has no evidence that the buffer is null here in this function. It could be anything. So it says for this dereference to be valid, buff must be not null. Now, our programmer, Peppa, is pretty happy with this because it's a simple bug. But it's difficult to track down later. And with that, I would like to summarize Lint-style checks that we just saw. They find defects quickly, and they are relatively cheap to locate and fix. They are built on syntax or simple flow analysis. And there are many successful Lint checks available in the community today. And so we have lots of happy customers using these Lint-style checks. Now, the challenge for us is how can we scale these Lint-style checks? One of the challenges is to make analysis scale across function boundaries, because we need to be able to get a view of the whole program to figure out some of the bugs. And there are two ways to do this. One is the interprocedural or the whole program analysis. And with that, we start with all the leaf level functions, and we track certain properties. We construct the properties we are interested in. Then we propagate these across the call chain. And it's slow. And when I say slow, it's not like minutes slow or hours slow. Depending on the size of in your code base, the simulation can take days. So it is best suited for outer loop. So it's best suited once your code has been merged. Maybe you're running some outer loop analysis, and then you are finding these bugs without any upfront cost, right? Because they have the view of the whole program. And they are great for specific problem domains. In fact, in Microsoft, we had a tool called Prefix, which was very effective in finding use after free without any annotations or any changes in the source program. The other approach is called the intraprocedural or local analysis, where we analyze across each function in isolation. So we explore different paths in the function, but we cannot see across function boundaries. And what happens is we try to infer the function called semantics from different things like types. If you are using a reference type, it's pretty reasonable for an analyzer to assume that it's not null because references cannot be null. Similarly, type extensions are also useful. You may be able to express a not null. In our guideline support library, there is a not null type extension. And if you put that in your code, it basically means that this entity can be, this function parameter can be assumed to be not null. We can also infer things from the modifier. So if you have a const, the pointer parameter in your function, it's pretty reasonable for analyzer to assume that you can't write to that. You can't modify something which is const. Similarly, you can apply heuristics. If you just see a pointer but nothing else on it, it's probably okay to assume it's like an in-out where it's probably okay to read from or write to. And lastly, you also have source annotations. And I'll show you some examples on what I mean here. The nice thing about this kind of analysis is it's very fast. It's best suited for inner loop where you can find your bugs very early. And it finds issues across a wide domain. So with that, I go back to my previous example where we found this buffer was never tested for nullness. And so what Pepa does is she's not sure whether all the callers would guarantee that the buff is not null. So she adds the defense in depth and checks for the null explicitly in her function and to guard against this null check. And she's pretty happy about it because it's cheap to locate and fix. Now, next she runs the analyzer again on her same code and she wants to see a green state and no problems with this. Unfortunately, the analyzer tells her something else. It tells her that there is a possible incorrect single element annotation on buffer. And there is a potential read overflow here using the buffer index. And at this point, she is confused because she can't see any annotation, but the analyzer is assuming that buffer is of size 1. But she has worked on this code base for a few years, and she knows that buffer is actually not size 1, but it's of size buff size. And but how does she express that in C++, right? How does she convince static analysis that buff is not one element, but it's actually buff size? So what happens next is she chances upon this header in the Windows SDK called sal.h, and you have these little bit esoteric notation here called in-reads, which essentially tells Pepa that, hey, you can express buffer size now using sal, which basically tells her that buff is of size, which tells the analyzer that buff is of size buff size. And so this way she's able to at least convince the analyzer to not treat buff as size 1, but of buff size. And with that, she runs analysis, and analysis finds an actual buffer overrun here. What the analyzer is telling Pepa now is, look, you're calling getIndex on this line, but what getIndex returns is not bound by the buff size. So it could return anything. It could return a number that is much larger than buff size. So if you try and fetch buff index, it could result in an overflow. So annotations actually helped Pepa find the real buffer overrun, but she's in a better world, but she's still not happy because she's figuring out, do we have to learn a new annotation language? And so with that, let's look into some of the pros and cons of annotations. So there are definitely some advantages. Annotations formalize your code documentation. A lot of times, we use comments to express what our functions do. But if we formalize them in some annotation form, then it gives the chance to static analysis to use that information and to analyze across function boundaries. So it's an effective strategy for static analysis tools. It also helps with API design. When you are writing your annotation from the very beginning, you have to think about how your callers are going to use your API. Because if you can't express these contracts, then how do you expect your callers to use your function correctly? And it provides some sort of an incremental ROI, so you can maybe look at certain parts of your code base, and then you can try and annotate that part which is more problematic, and then lock in that work, and maybe add some later. Maybe you can build some inference engines, so there are definitely some advantages there. But it also has several disadvantages. One, annotations are non-portable. Like the sal that I showed you is an extension. It doesn't work across tool chains. So you can't reap the benefits, especially when you're sharing code into this world. It quickly explodes in source code. Once you start adding annotations, they're viral in nature. You quickly start seeing them all across the code base. And they are not the ultimate source of truth because you may end up changing the behavior of the function. Maybe you change the definition, but then you don't end up updating the annotations. So that will mislead analysis because you haven't done the due diligence there. And it's only as good as the tools. If you add annotations, but the tools are not smart enough to take advantage of them, then what's the point? So with that, Pepa looks at our guideline support library, and she looks at this type called GSL span. For those of you that are not familiar with GSL span, but are familiar with the C++20 standard span, GSL span is essentially equivalent to standard span with one additional safety guarantee in that when you're trying to access out of bounds, GSL span would terminate your program. So you can never read past the bounds. For those of you that are not familiar with the span type, it's essentially a data structure with a pointer that points to the beginning of a buffer and an extent. So if you pass this type along across your functions, it's very easy for static analysis to figure out whether you are writing within the bounds of that buffer or not. So in this example, Pepa changes the signature of fetch element to take a span of integers. She then calls getIndex, and she wants to be defensive. So she adds an if check to make sure that index is within the size of the buffer, and then she accesses buffer index. Now, this is the C++20 way to write the same code, right? It's range checked at runtime, and even if you didn't have the if guard, we will warn statically. And your program will terminate at runtime if you do end up accessing out of bounds. So what we saw is we started with lint checks, and then we started with how we scale the lint checks. We started with some annotations, and here is a type and type extension that can be used for making your program safe. Pepa realizes type extensions are great. They are portable, and they can be checked by the compiler. And with minimal cost, runtime checks become possible. With that, I'll show you one other example, which is not a buffer overflow in itself, but a different variant to that same problem. In this example, this is actually a real-world code from the DNS server. What's happening here is we are trying to read a signature across the wire. Now, a signature has three parts. It has a fixed data. It has the name of the signer, and then it has the signature. And what we are doing here is we are allocating the buffer by adding the fixed data, the count of the name of the signer, and the signature length. And then we are doing a mem copy. We are trying to write the output record, trying to copy the signature by copying signature length bytes into the buffer. What happens here is when we do the allocation and we are adding the three entities, like the size of the fixed data, the count of the name of the signer, and the signature length, there is a arithmetic overflow that happens here, and we end up with a buffer of much smaller size. So when we are trying to mem copy, we actually are writing past the end of the buffer here. And this was a heap overflow in the DNS server, which was actually caused by integer truncation. The sum overflowed, causing our output record to be nearly 0 bytes during mem copy. So not all arithmetic overflows are the same. Some can cause pretty nasty security bugs out there in the field, and this is one such example. And this is a check that we have a checker that detects all these arithmetic overflows that get used in allocation. And we have received pretty good feedback from the security team, and we plan to make this available in GitHub and Visual Studio in the future. And this is my last example for today, where it's not just null pointer dereference or buffer overruns. We also find subtle concurrency issues, especially when you try and use new language features. So coroutines got added into the language in C++20, and here is an example of a function that acquires a lock and then suspends a coroutine. And what we end up doing here is we weren't saying that you are really suspending your yielding while a global lock is held. And actually, this can be pretty bad because if there is another thread that's waiting for that lock to be released, it can cause deadlocks. So deadlocks are hard to detect when it comes to debugging. So we can use static analysis to also prevent unsafe uses of new language constructs. With that, I would like to talk a little bit about the static analysis framework that we use. We have the C++ frontend that we rely on to parse the file. It ensures we have valid syntax, and it produces the compiler trees, we call them ASTs, that essentially represent source code for us. And on top of that, we have an abstraction called prefast, and it serves several purposes. It acts as an interface between the compiler front end and all the analyzers that want to check for certain properties in the program. So as an analyzer, you can sign up for callbacks when you, for example, see a function definition or declaration. And once you have registered for these callbacks and prefast sees these being parsed by the front end, it will call you. You can do some work, find defects, report it back to prefast, and then prefast will emit this defect for you. So it also has a defect manager. Prefast also has its own internal set of checks, so it can also find issues for you which are mostly syntactic and with some checks are written on simple flow analysis there. On top of Prefast, we have Usbx Engine. What Usbx Engine does is it transforms the trees to simulate function execution. So it represents your program as control flow graphs. And this is the part that does a lot of heavy lifting when it comes to doing data flow analysis or path-sensitive analysis. And it has a number of extensions that can get called back by the engine once it has constructed the CFGs. And these extensions can track their own properties as Usbx Engine is walking different paths. So this layer has a lot of useful libraries. It can do symbolic state tracking. It has a fast linear constraint solver. It can do alias analysis. It does loop widening. A lot of this heavy lifting is done by the engine. In the past, this used to be done by each and every checker separately. So there was a lot of repeated tasks that was done. And what we have done now is put everything in the engine layer, and then we have different extensions. Extension 1 is maybe looking for concurrency defects. Extension 2 maybe is looking for buffer overruns. So this is the model that we have based our framework on. And there is a talk on Thursday by Gabor that will walk you through how you can find bugs using path-sensitive static analysis. And for those of you that are interested to learn more about this, I would strongly encourage you to attend that talk. So with that, I would like to go over where we are today. So static analysis today, it's in use at Microsoft for nearly 2 decades. And it started with Lint-style checks, and we can find a lot more now compared to how it was a few years back. It's built on many years of research. I think what you saw here, the prefast layer itself started as a project in Microsoft Research. Then it moved to a division called Center for Software Excellence. And during Windows Vista, it was funded by the Windows group. And now, since we work so closely with developers, we are part of the Visual C++ offering, and we work very closely with the compiler and the community to write these safety checks. We have used these tools to validate millions of lines of C++ code in production software. And they are available in all editions of Visual Studio and GitHub Action. So if you are contributing to an open source project in GitHub, and this is the first time you can, since it's Cmake based, you can try these tools no matter what toolchain you're using. So static analysis finds bugs, and it's free, and you should use it. And like I talked about at the very beginning, by finding bugs early, you can save some dollars. And since I work from one of the large corporations, anytime we can save dollars, that's really a good thing to do. So you should really consider using it. So what's next for us? We definitely want to invest in more safety checks. We want to, for example, some of the buffer overrun checks, a couple of examples that I showed you, they are not available in Visual Studio or GitHub yet. So we want that to be made available. We have a null pointer dereference check, but that's noisy. And we want to improve that, and we want to ship a much more accurate version of the null pointer dereference that understands not just the context from the code, but also guideline support library, things like GSL not null. Arithmetic overflow in allocators is something that we have been evaluating, and this is something we would like to ship. There are interesting memory leaks, so you can mark memory that you own as GSL owner, and our analyzer should be able to find leaks where a non-owner is trying to, for example, delete a memory that it doesn't own. And we have some checks that find uninit bugs, but there can be subtle uninit bugs in code. Like you can, for example, when you use std optional, you can end up reading uninitialized memory if you are inadvertently dereferencing that type. So we want to build checks that detect more nuanced cases of uninitialized memory access. And we have lifetime checks. Few of them are part of the default rule set in Visual Studio and GitHub, but some are kind of noisy, and so we have kept them as experimental. We want to work and improve those, and we want to ship them as part of the non-experimental rule set in Visual Studio and GitHub. Similarly, we want to improve our concurrency checks to find issues as new language features get used. With that, supporting new language features is also extremely important. So like I showed you, with coroutines, we added a few checks that could lead you to bugs if you used coroutines incorrectly. And so, and similarly for modules, for example, we work closely with Gabby and Cameron to make sure that analysis artifacts could be preserved as you export and import the modules. We are very hopeful that we will have code contracts in the not so distant future, where hopefully a lot of the preconditions, postconditions, and invariants can be expressed. And we can maybe take advantage of that in a way that works across platforms. So I'm looking forward for that to happen. We also care a lot about accuracy and speed. So our goal is to minimize false positives, and it's largely driven by feedback from the community. So every release, you will find our team does a blog that basically talks about all the accuracy and speed improvements that we do. So if you go back and read the VC blog, starting with 16.9, 10, 16.11, we have documented the kind of accuracy and speed improvements that we have made. And we did a quick experiment with the OS team in Azure to see, to measure some of these improvements. And over the last couple of releases, our checkers have been 45% faster in the OS repo. And so that's something we constantly try to do, so that you're not paying any more price than you have to for doing such analysis. We want to make Analyzer more understandable. It's key that what we produce is understandable to every programmer. So what you saw in the earlier demos, the key events, is only available today on a subset of warnings. We don't have that for everything. And what we want to do is we want to create a key events infrastructure in the engine, so that anytime you write a path-sensitive extension, you get key events for free. And so one of the challenges with path-sensitive checks is they're difficult to reason about. When you see a bug, you have to work your head to figure out, is this really a bug? Or is the analyzer confused? Or maybe it's not aware of some hidden assumptions. With key events, it's very explicit, because you can see what the analyzer is thinking, and it becomes easy for you to determine if it's a bug or if you have to pass some information to the analyzer. We also want results to be customizable. So we shipped a flag called external that allows you to eliminate warnings from any external includes in your project. You only get to see what you build. You get to choose what rules you want to build with. We have a set of defaults, but it's configurable. You can turn on and off rules. But I would say, start with the defaults. They provide a lot of value. Like we have C++ core guidelines that has every possible rule in the guideline, but we also have specific profiles like C++ type safety rules or lifetime safety rules or bound safety rules. So you can start with these profiles if those are the bugs you want to catch. And we also want to make filtering better. Like I showed you in GitHub, it's super easy to filter warnings, and we want to invest in making that even better, both on GitHub and Visual Studio. And our North Star is to make static analysis universally available. So one of the good things about static analysis is you have a lot of choice today, but what is available on one tool isn't available on another. And it is actually a disservice to the developer community, because we have a lot of smart checks, but what's the point if you're not able to access these checks in your tool chain, in your platform? So I think we are very passionate about static analysis, and we want to make sure that what we have can be accessed everywhere. I think it would be like a massive advantage to the entire developer community if we can do that. And we have started some work very early to talk about towards that effort. And hopefully in the coming days, I can come back and share some of the things that we are doing to make this experience universal no matter what toolchain you're using or what platform you're on. And lastly, you should join the fun. A lot of the work that we do is heavily influenced by your feedback. Please contribute. You can suggest us checks, bug reports, any fixes you would like to offer, tests, any ideas. You go to Visual Studio Feedback. You can file a feedback or a suggestion, and based on the upvotes and the severity, that's our guiding principle when it comes to prioritization. Similarly, if you have changes you can offer to the core guidelines, like I said, you may not get a overnight turnaround, but we have had a lot of success working with the core guideline editors, and so that's definitely one of the guiding principles that we use. So I would also ask you to go and contribute there. With that, I want to leave you with some final resources. Go read our blog on the GitHub Actions, where you can try out these checks in GitHub. I've given you a pointer to our team blog where most of what we do is announced. There is a documentation in MS Docs where you can read about code analysis. For those of you that have not tried out Lang-tidy, it's a fantastic tool with fix-it capability. So go try it out if you haven't already. There is like I said, go to CPP core guidelines and engage in conversations. Contribute to the guideline support library. We meet on a fairly regular cadence, and we try to address most of the issues that come through from the community. So if you want to see a specific type extension improved or added, let us know in the GSL repo in GitHub. And if you're interested to learn more about Serif, the log format, and write your own actions in GitHub, you can learn more about that at the Serif Foundation. I've provided a link to that in my resources. Yeah, that's all I had. Enjoy the rest of the conference. Like I said, we have a booth where you can meet the C++ team at Microsoft and discuss anything that you have read about. You can also enjoy some of the other sessions that we are doing. We have sessions lined up for today, tomorrow, as well as Thursday. In fact, Gabby is talking about in-memory persistent representations of C++ right after this talk. Tomorrow you can talk about, we are talking about what's new in Visual Studio. So Sai and Marian is doing that talk Thursday. Mia is talking about C++ 20's Chrono feature. Julia is talking about debugging assembly language, GPU kernels in VS Code. Charlie is talking about std format, and Gabor is talking about finding bugs using path-sensitive analysis. So we have a pretty packed lineup, and I would encourage all of you to go and attend these sessions and let us know what you think using that survey link. And I can take some questions now.
There's a question online.
Okay.
If there is a report that I want to mark as won't fix, false positive, can static analyzers stop reporting those instances in subsequent analysis?
So if that functionality that I showed in GitHub, the answer is yes. If the branch owner marks them as false positive or won't fix, then those instances will not be reported again in the GitHub workflow. Correct. Sure, go ahead.
Follow-up question. How does it know that it's the same problem?
So the question is, how does it know it's the same problem?
The lines change, the function gets renamed.
Yes, so the way it works is it tries to compute a hash, and there are a number of inputs to compute the hash. It could be the source line itself where the defect appears. It could also be, like you said, if the hash function takes into consideration the function name, that's pretty fragile because anytime you refactor and rename the function, your baseline will be off and you will start reporting that warning again. So most of what is done is you look at the exact source line and compute a hash based on that source line. But there are hashing strategies that also take into account file name and function name. It's like a trade-off. But in this case, what we do is we compute a hash using the line itself. And as long as the hashes match, we will not report it. All right, we have another online question there.
We have another online question. What are the chances to get the new GitHub Actions supported beyond Cmake?
Okay, so the question is, what would it take for us to support the GitHub Actions beyond Cmake? Like I said, the work that we do is heavily influenced by the community and the feedback that you provide. What we have done is we have created a suggestion ticket where you can go and upvote other build formats. So if you want to see this experience on, for example, native MS build support, I would strongly encourage you all to go and click that upvote so that then my team can pick that up and that can get prioritized and we can bring a native MS build support to you guys. Sure.
Control the severity of the box. Because we used the static analysis before, and then could come out so many like overwhelming number of the messages, and we want to turn off some messages. Is that be done?
Sure, I think it's a great question. So the question is there a knob to control the severity of the warnings that get reported? Because in the past, when you have tried to turn on static analysis, you got into this wall of bug problems. You have like hundreds of them, and you get overwhelmed, and you don't know where to start. I think that's one of the one of the challenges of doing static analysis right is to just look at the code that introduced a bug right then, because you can't fix the baseline that already exists in the code base. So with GitHub, like you saw, and you have a main branch, as the branch owner, only I get to see the backlog. But when I have contributors contributing to that branch and creating PRs for that branch, they only see what the PRs are introducing and nothing else. So as a developer, when you're contributing to a project in GitHub, and if you introduce 5 defects, you will just see those 5 and not anything else. But as the branch owner, I will have the complete view so that I know that this is my backlog. And maybe at some point, I would want to distribute that in the community and get it fixed. But I think the GitHub experience really makes the baselining easy because you only see issues in your own code, in your own PR, and you don't run into this wall of bug problems. On Visual Studio side, we have done a few things. So one of the things we have done is you can now eliminate any warnings from headers that get included in your project that you don't directly own. So you can see only stuff that you own. And you can also configure the warnings themselves. So you maybe want to start with the defaults, but if you see that there are certain classes of warnings that are more prevalent in your code base, you maybe can turn those off. So you can create a custom rule set that can turn rules on and off. And you can do that in both Visual Studio and GitHub. But then you have a few knobs there. You can control using the set of rules that you run on. And you can also control that in GitHub using the defects that show up just for your pull request. We don't have a baselining facility in Visual Studio. But if you would, again, love to see that, then provide us feedback, and we can definitely put that into our backlog and execute on that. All right. Sure, go ahead.
So you mentioned false positives being a challenge.
Mm-hmm.
A lot of times that's due to just a lack of annotation or typing in the code. And a lot of times the engineer can enhance the source file to give that context. Have you all considered proposing any kind of changes to the C++ language itself so that those annotations can be portable or at least harmless in cross-platform situations?
Okay, so let me repeat the question. So what you're saying is a lot of the times false positives are not because the tool is wrong, it's because there is a programmer intent that's not expressed in code. And have we done something to make those intents be expressible in the standard language by moving some of the annotations to the standards? And I think a very good example for that would be one of the things that I just showed, like standard span. I think it all started with, we had our own Microsoft SAL, and like I said, it was esoteric, and I was very respected in the company because I knew a lot about SAL. But when it came to explaining, I figured that it's not the most friendly way to express the intent. So I think we pursued a direction where we wanted to get this in the language. So Guideline support library is our first stop there. We worked with the core guideline editors. We had a type called the GSL span type, and we had an implementation. And we used that internally in production code. And we found lots of real security defects that were caught. And then it made its way into the standard, and we have a standard type today, which is called the standard span. So we definitely, if we do a good job, I would love to see GSL go away, and most of the concepts we have in GSL hopefully make it to the standard, but it's a long journey. And what we do with GSL is use these extensions, study its viability, like whether they make sense to be in the standard, and then pursue that. But it's like, it's definitely, that's an organic way we are developing these in today. That makes sense. Okay, so you have two questions. One is whether the tool has defects that can point out deficiencies in the object-oriented design. And the second is if it can detect memory leaks. So the answer to both of that is yes. If you look at core guidelines, there are specific rules that guide you to write object-oriented programming in the right way. I can give you an example, for example. So if you have defined, for example, one of the standard 5 operations on your class, but not the others. And if you write the core guide, if you run the CPP core check extension, which is on by default, you will find that we will tell you, hey, you've defined one of the 5 operations, you should also define the assignment, the copy, and the move, and all of that, because that's a good discipline to have in object-oriented design. So there are many other rules like that. So I would say, go take a look at the core guidelines and then try out these checks in the GitHub or Visual Studio. And you will find a lot of the times we can guide you to write object-oriented code in the right way. And the second thing is whether it's possible to find memory leaks. So like I said, it's challenging to do as far as local analysis is concerned. So we have rules from the guidelines that we enforce, like whenever possible, you should be really using unique pointer and share pointers and not worry about your own memory management. But we realize there are cases where you have to do that. And so we have an annotation, again, it's prescribed in the core guidelines called owner that we try to enforce using our analysis tools. So you can have a memory management discipline enforced in your code. Functions that are creating the memory, only they are able to delete it. So you use owner annotations there, and when you're passing to a function as a non-owner, that function you're calling has no right to delete that piece of memory. Now, if you want that function that you are calling to delete the memory, you pass the ownership to the call function. So then you put that magic type extension, GSL owner, think of it like an annotation, but it works across platforms to that call function. And then the call function can delete the memory because now ownership has been transferred. But on the caller side, you can no longer access that memory because that's no longer assumed to be valid because you've transferred the ownership and the call function could have deleted it. So there are many checks like that. Similarly, there are lifetime checks. Yesterday, Bjorn has an example of how when you are writing to a vector and you have a pointer, a raw pointer to its first element, then you call a function which pushes back to the vector and it changes its memory layout. From the type, we can infer that since it's a reference type, underlying object can change. So we assume that that pointer is no longer valid. So if you do a pushback, and if you try to dereference to the pointer that you had that was pointing to the beginning of a vector, we will warn, our lifetime checks will warn and say, hey, that memory is no longer valid. So you can definitely try these. There is a lifetime profile in Visual Studio and in GitHub that you can try and give us feedback and we can make it better. Yes. Sure. So the question is, the checks that we have in GitHub, are there any plans to put these checks in Azure Devops? So we don't have anything planned as of yet for Azure Devops. We do have an internal experience for Azure Devops. It's called the Guardian module, which tries to run different analysis, security analysis tools inside. And that has been integrated with Azure DevOps. But if this is something that you want to see in Azure DevOps, especially for the external community, again, you can file a suggestion ticket, and we use that our guiding principle, so we can definitely add it back. But right now, we are not planning to add anything on top of Azure DevOps. Any other? Okay, we have another question online. Oh, okay, the session is over. All right, thank you everybody for being here, and I'm looking forward to your feedback.